Hi, BC Calc. These are your day 89 notes. Today we're going to be talking about a really important integration technique called integration by parts. Before we get there, we're going to do two practice examples. And I usually say, hey, let's try these or we'll do them tomorrow. I'm going to do the first one with you in the notes today, and then I'll have example two be one that maybe you try on your own here. So they're cool applications that will involve some integrals that we now know how to find. And you'll see what I mean in a moment. We're going to find the length of the semicircle y equals radical 1 minus x squared from -1/2 to +1/2. So if we think about that semicircle with radius 1 centered at the origin, from -1 to 1, we would get this semicircular region right here. And what we want to do is we want to find the length from -1/2 to +1/2, like this. Okay, so we certainly have some symmetry going on here. But we got to remember that arc length formula. So if you remember for arc length, the length along that piece up there, the length from A to B is going to equal the antiderivative from A to B of the square root of 1 plus dy dx squared with respect to x. Okay. So we have to find dy dx. We're going to plug it in, square it, and then hopefully simplify what's underneath that radical, and some nice things will start to happen here. So let's talk about dy dx first and foremost. Dy dx would equal, if I use, you're going to have to use chain rule here, right? It's going to be 1/2 and then this quantity to the -1/2. So that, when I get rid of the negative exponent, would be 1/2 radical 1 minus x squared, but then times derivative of the inside for that chain rule piece, which would be -2x. And you'll see that these twos cancel out. So the derivative of y equals radical 1 minus x squared is -x over the square root of 1 minus x squared. Now keep in mind, we're going to square that when I put it into the arc length formula. So if I square dy dx, that would equal -x squared, which is going to be x squared here. And then squaring the radical in the denominator, that's just 1 minus x squared for a quantity down there. So putting all the pieces together, if I now apply the arc length formula, I'm going to go from -1/2 to +1/2, although you can probably accomplish the same thing by doubling 0 to 1/2 here. And then we're going to do the square root of 1 plus dy dx squared, so that's going to be x squared over 1 minus x squared dx. And what we'll notice here is if we go ahead and make this into a common denominator, if this was 1 minus x squared over 1 minus x squared, 1 minus x squared plus x squared is going to leave just a 1 up in the numerator there over the LCD of 1 minus x squared. So some interesting things start to take place now. Again, this step to this step was making a common denominator, 1 minus x squared over 1 minus x squared. Adding the fractions together, the numerator is just 1 now. Well, isn't that really just 1 over radical 1 minus x squared? What? We know that antiderivative. We can find it pretty easily. The antiderivative of 1 over radical 1 minus x squared is what we now know and love to be sine inverse of x. Oops, I got a little excited there. Sine to the -1 of x. And we're integrating over the bounds from -1/2 to +1/2. So we got to do sine inverse of 1/2 first. Sine inverse of 1/2 is pi over 6 minus sine inverse of -1/2. So remember, that's going to bring you into quadrant 4 and get you an answer of -pi over 6. And when I then add those together, pi over 6 plus pi over 6 is 2 pi over 6, which reduces to a final answer, just about squeezed it in there. Pi over 3 is the exact arc length of this part of the semicircle. How cool is that? Right? Bringing back some good old arc length formulas, but now an antiderivative that we know how to find. We don't need the calculator. We can get an exact answer, in fact. So I'll have you at least try the setup here. If you feel like, yep, I've got the idea and I'm going to be able to find the volume when revolving this equation bound over these values of x, we're going to rotate it around the x-axis. Okay, so find that solid of revolutions volume. If you think you've got it, I mean, make a quick sketch at the very least. I think you guys can handle this one. It's a little bit cleaner even, I think, than the one that was just up above with arc length. All right. But now we're actually going to get into the good stuff for today. Day 89's focus is, again, all about our new technique of integration by parts. When do we use integration by parts? It's used when we're integrating some products where U sub is not available to us. So when we see the product of two quantities, sometimes a U substitution is necessary and helpful in order to be able to go ahead and evaluate the integral. That's not always the case, though. So since it's an application of where we would have product rule in a derivative sense, we know that the derivative with respect to x of a product uv is going to be the first times the derivative of the second plus the second times the derivative of the first, according to product rule. And that each of those could be expressed as, when I talk about v prime, you know, we're taking the derivative of v with respect to x. So this is really dv dx, and this is really du dx over here. Okay, so that's just kind of writing up the product rule here. So from there, what we want to do is, just to kind of clean this up a little bit, I'm going to multiply the dx out of both sides. Okay, so we're going to kind of write this in terms of differentials. So d of the product u times v would equal u dv plus v du. And we're using our product rule here to be able to generate a rule for integrating a product. What we're going to do with this step is we're going to introduce an integral along the way here. Okay, so the integral of the derivative of u times v, isn't that just u times v, right? And on the other side, we get integral of u dv plus the integral of v du. In the very last step, I'm going to get u dv alone by just subtracting this integral to the other side. So what we have is that the integral of u dv is equal to the product u times v minus the integral v du. So that last step again was just subtracting this to the other side. And if we have a product of two quantities, we're going to try and assign one to be our u and one to be our dv. And then within there, see if we can write it as this equivalent expression where we have u times v minus the integral of v du. So this is the general rule that we are trying to build towards, that the integral of u dv, the product of two things that u sub is not available for you, is equivalent to, according to our derivation there, the product of u and v minus the integral of v du. And this will start to make more sense when we put it to practice, but I'll tell you what our goal should be. Our goal is when we decide what u and our dv are within the product on the inside of the integral there, we want to make sure that what's on the other side, that v du, is easier to figure out than u dv. Okay? Because if not, we may have to switch on what we call u and what we call the dv. All right, but this, in theory, in order to be able to evaluate this and figure out what the integral of that product is, we want v du to be easier than the reverse u dv. If not, we'll do a switch. All right, so let me show you what that looks like for the first example. We have the integral of x cos x dx. So if we think about u substitution, what would I call u? I mean, I can't call u cosine of x. I can't call u x. The du would not necessarily line up nicely such that we can use u substitution as is. So what we need to do is we have to decide on a column of terms that we're going to differentiate. And the way we're going to set this up is we're going to have a column for differentiation and then a different column for integrating. Because what you'll notice is when I decide what's u and what's dv, on the other side I'm going to have a du, and I'm also going to have a v that we have to put inside the integral here. So I think at a quick glance, what would make sense for this example is let's let u equal this quantity x, because then du is quite simply dx. On the other side, I'm going to let dv equal the remaining quantity cosine of x dx. Okay, so here's our u, here's our dv. So you can see how that product is what we have, and that's what we're trying to integrate. And if that's what dv equals, we know that v is pretty easy to come by, right? We know the integral of cosine of x dx. So the integral of cos x is just sine x. And if you set up these nice columns for the differentiation column and the integration column, you then get this kind of like arrowed pattern here where the integral of x cosine x dx, if this is u and this is the dv part, can be written as u times v. So that's this connection right here, right? U times v. So that would be x times sine x minus the integral of v du, which is sine x dx. And because this integral over here is pretty easy for us to evaluate, we're one quick step away from getting the final integral. So this would be x sine x, and the integral of sine is going to be negative cos. So then this is going to be minus a negative cos, would turn into plus cos. And therefore we have a plus c at the end there. Okay. So the integral of x cos x dx in its initial form using integration by parts would turn out to be x sine x plus cosine x, and of course plus c for the indefinite integral. Well, if you're ever unsure, like, hey, does this even make sense? Can I check with the derivative? You need product rule there, right? Derivative of cos, negative sine, but what you're going to find is that you're going to get some sines to cancel out, and you will just be left with x cosine x, which is kind of nice. So you can do a quick check with the derivative, especially for ones that are pretty easy to work with, just to make sure that your answer in the end makes sense and that you've done the integration by parts correctly here. All right, the next example is a follow-up to that. So if I have the definite integral from 0 to pi over 4 of x cos x dx, well, the integral that we just found for x cosine x is x sine x plus cos x. And then you're just going to integrate from the upper bound of pi over 4 to 0. So we don't have to refine that integral again, but if you were faced with something like this initially, we would need integration by parts, of course. All right, so if I plug in here, let's see if x is pi over 4, you get pi over 4 times sine of pi over 4, which is 1 over radical 2, or if you like the rationalized radical 2 over 2 better, you can get there. Plus cosine of pi over 4 is also radical 2 over 2. Minus, when you plug in 0 for all the x's, this is 0, but cosine of 0 is 1. And cleaning everything up here, this is going to be radical 2 over 8 plus, radical 2 pi, sorry, radical 2 over 2, and then minus 1. And that's pretty much as exact as we can get. If you want to kind of pull it all into one fraction here, you would need common denominator of 8. So this one would need 8 over 8 at the end here. So it looks like we're going to have radical 2 pi plus 4 radical 2. If you want to get fancy, you can even bring the radical 2 out in front of pi plus 4 minus 8 all over 8. That is an exact form for the definite integral that we were given at the start of example 2. All right, it takes a little bit of practice, by the way, to get good at identifying what do you want u to equal and what do you want the dv part to equal. So if you don't make a good choice, you're going to figure it out really quickly, because look what happens in this example here. If I call this u and I call this the dv, so u would equal x and du is dx. Looks like just the start of the last one. Well, for dv, we're saying that that's ln of x dx. So therefore, v equals, I don't know. We don't know the integral for ln x yet, right? Think carefully about that. We don't know v. So if that's the case, then you're going to have to switch it. You're going to have to let u equal ln x, and then you're going to have to let dv equal the x dx. So let's kind of think of this differently here. If u equals ln of x, then we know that du is 1 over x dx. dv, we were saying, should be now x dx. So therefore, v is equal to, the integral of x would be x squared over 2. And since I can find that integral, let's see if we can go ahead and use our integration by parts to do u times v minus the integral v du. So u times v is going to be x squared over 2 times the natural log of x minus the integral of x squared over 2 times 1 over x dx. Okay, the v du is going to go on the inside here. Then we can clean that up, right? This x cancels with one of those x's. So we're going to get x squared over 2 ln x minus the integral of, that's just going to become x over 2 there, dx. So if I up that by 1, x squared, and then divide by 2 out front, we're going to get our final answer here for the integral of x ln x dx, the original, to be x squared over 2 ln x minus, this would turn into x squared over 4. And then, of course, don't forget about plus c. So with more practice, like I said, you're going to become good at picking out, I hope, the u and the dv that works the best. But if you pick one that doesn't work, you're probably going to find that pretty quickly at the beginning of the process. There's a lot more integration by parts to come. When we get to class, we're going to do some of these for practice that are down below for the day 89 homework here. But I think this is a pretty solid introduction to the whole process of integration by parts. If you have any questions about what was in day 89, you'll let me know next time I see you. Have a great rest of your day.